So section 2.3 is all about this main theorem. There are infinitely many prime numbers, and we need to study why that's true. Now, a couple things. One, we've known about this theorem for a really long time. In fact, this guy Euclid proved it in 300 BCE. So thousands of years ago, we proved this theorem. And a second thing is, you might be thinking that this is common sense, that there's infinitely many numbers, therefore there's infinitely many prime numbers. But if you were to look at a table of prime numbers, they get more and more spread out. Like, what if they run out? What if there's only like a billion prime numbers and then all of the other numbers are based on those? We don't know. So we have to prove this using hardcore logic. So I want to outline this proof for you. If you name any number you want, I will prove that there's a prime number bigger than that number. And we're going to start with 2, which seems kind of silly because obviously 2 is not the biggest prime, but let's start there anyway. So you get to name the number, and then I will calculate this number. It's 1 times 2 times 3 all the way up to n plus 1 after that. You might recognize this as n factorial, right? Where you multiply all of the numbers 1 through n. So this is n factorial plus 1. So if you said n was equal to 2, if you make that declaration, then this is what I compute. 1 times 2, which is 2, and then I add 1, so I get 3. If you said n was 3, I would figure out 3 factorial, which is 6, and then I would add 1 to get 7. If you said n was 4, I would find 4 factorial, which is 24, and I would add 1 to get 25. If n is 5, you can figure out 5 factorial, which is actually 120, and then you add 1 to get 121. And if n is 6, you do 6 factorial plus 1, which is 721. So let's say that n is not 2, 3, 4, 5, 6. Let's say n is huge, that you get really daring and you say n is 1,000,000. Here's what I'm going to do. I'm going to form an even huger number m, which is going to be n factorial plus 1. You multiply all the numbers up to n and then you add 1. Now, I'm going to claim that my number, I don't know if it's prime or composite, but there's only 2 things that are going to happen. Either my giant number m is prime, that could happen, or the prime factors of m are even going to be bigger than it. Like, my number is going to be so big that even its prime factors are going to be bigger than your n number. And I'm going to explain why. If you were to divide m by any number between 1 and n, you're going to get a remainder of 1, which means that m can't be divisible by any little puny number between 1 and n, which means it has to be divisible by bigger numbers. So here's another way of seeing it. You claim that the number 2 is the biggest prime in the world. And I say, nope. 1 times 2 plus 1 is 3. And that is just straight up prime, and it's bigger than your number. And then you say, fine, 3 is the biggest prime in the world. And I say, nope. 1 times 2 times 3 plus 1 is 7, which is a straight up prime number, and it's bigger than your number. So I beat you again, and you say, fine, 7 is the biggest prime in the world. And I say, 7 factorial plus 1 is 5,041. Now, that's not a prime number, but 5,041 is 71 times 71, right? And 71 is prime, and 71 is bigger than your number. So I beat you again. And then you're like, fine, 71 is the biggest prime in the world. And I'm like, I'm not having this conversation anymore.